Okay, we are now live. No, here, please.
Thanks.
There you go.
All right. Okay, so yeah, I'm going to talk about intuitionistic modal logic. And I'm gonna we're gonna look at several different approaches to intuitionistic modal logic, but the one that we're going to focus on the most is the approach of Alex Simpson, as in his 1994 PhD thesis. And this is an interesting approach because it kind of has two sub-approaches. One is can be thought of as formalizing the usual key semantics of modal logic in an intuitionistic meta-theory, and the other is a more proof-theoretic definition of intuitionistic modal logic. That is, he gives a natural deduction system in which the possible world's interpretation of the modalities is built into the inference rules. And interestingly, it turns out that these approaches are equivalent in a way that we'll make precise later. So before we get to that approach, we'll survey some early approaches. But before we get to that, I'd like to consider some requirements that we might have of a intuitionistic modal logic. Am I able to use the whiteboard?
Yeah.
Yeah. Just because I think it might be helpful to have these. Okay, so classical propositional modal logic is classical insofar as its non-modal fragment is just classical propositional logic. So it seems kind of uncontroversial to require the analogous thing with intuitionistic modal logic. So our first requirement is going to be that intuitionistic modal logic, IML, is conservative over intuitionistic propositional logic. Yeah. Related and also fairly uncontroversial is that the usual intuitionistic reasoning should be available for the whole of the language, so formulas containing modalities as well. So we get the condition, the second condition, intuitionistic modal logic contains all subsets of theorems of intuitionistic propositional logic and is closed in the mode experience. Is that readable? Okay. Also, a general feature of intuitionistic logics is that adding the schema for the law of excluded middle gives rise to a corresponding classical logic. So you require the same thing for IML. So IML plus LEM gives classical modal logic.
May I interrupt with a question?
Yeah.
So classically, there are many different modal logics. They're like S4, T, S5. Are you working towards any one of those in particular, or general framework for modal logics?
Yeah. So this is at the moment I'm just talking generally. When we move on to Simpson's approach, the axiomatization he gives of his natural deduction system is he considers to be the intuitionistic analog of K, like the minimal modal logic.
Great.
But I guess this all makes sense. Just
it makes sense, yeah, for anyone, yeah.
Right. Yeah. Thanks. The fourth requirement, to be in line with constructive reasoning, we want that if A or B is a theorem, of intuitionistic modal logic, then either A is theorem of or B is. Yeah, again, you might regard all of these as pretty uncontroversial, certainly the first two. But so far we haven't considered conditions that we might put on the modalities. A condition we might have on these is analogous to the quantifiers in intuitionistic modal logic and to conjunction and disjunction. That is that in intuitionistic logic, these are independent of each other. I mean, existential quantifier is independent of universal, and an or are independent in that they can't be defined in terms of each other. Insofar as box or necessity or whatever you want to call it is to be considered as like a universal type modality, and diamond is existential, you might think the same is going to hold of the modalities. That is that they are independent. So and then the sixth condition is just that we would like an intuitionistically comprehensible meaning for the modalities, so I guess the semantics, and we want semantics with respect to which IML is sounding complete. We want
May I interrupt again? I think that this last point that it's going to depend a lot on what you want the modalities to accomplish, right? Whether
Yeah.
you want to have something like possibility and necessity, or permissible and required, or
Yeah.
no ability,
Knowledge.
or something like that, or something completely different, computability, or
Yeah.
there are so many different uses of modalities.
Mhm.
It's going to be difficult to have one.
Yeah. So yeah, this is kind of, I mean, this is meant to be somewhat vague.
Yeah. But in any particular case, it would be nice to have something like that.
Right. Yeah.
Yeah.
Yeah. Yeah. I guess. Yeah, that's a good point. Okay. Yeah. So we have these to refer to now for considering some different modal logics. Okay. So as you all know, Kripke semantics for modal logic appeals to structures of the form P, and then Kripke semantics for intuitionistic logic appeals to models of the form W, and then some ordering relation. Where R is a binary relation on W, and this is a partial ordering on W. So a natural thing to do is to consider for intuitionistic modal logic structures of the form W, R, the ordering relation. And the interpretation of non-modal connectives you'd expect to be just the same as usual. So the question is, how should we interpret modal formula? So one suggestion is So first we're going to look at the diamond free fragment. So how should we define the interpretation of formula with the box modal? One suggestion is that box phi is forced or satisfied or whatever, and a world if and only if for all v w of v implies let's call this one. So this is just the usual Kripke, the satisfaction clause for box in Kripke semantics for modal logic. But if we take this, then there's no reason why the usual monotonicity property for intuitionistic logic should hold. There's no reason, so I can write it down to remind you. There's no reason why for any W prime greater than W, we should have the W prime satisfies box A, given that W. So yeah, maybe okay as a first pass, but we want to try and we want monotonicity to hold. So one way to ensure that is to manually require that monotonicity hold by building it into the satisfaction clause. So Oh, sorry, no, I'm getting ahead of myself. So we could, rather than building it into the satisfaction clause, we could just impose a condition on the frames. And the relevant condition here, such that monotonicity would still hold, is that if you there is V such that so if we add this condition, if we make this condition of the frames, then monotonicity does hold with this satisfaction clause. Yeah, and like I gave away just before, instead of imposing a condition on the frames, we could instead build a condition just into the satisfaction relation. So the obvious condition would be you might notice as well there's an analogy here between there's an analogy between this interpretation and the interpretation for the universal quantifier in intuitionistic logic with Kripke semantics. So that's nice, I guess. So how might we choose between 1 and 3, or 1 with the additional condition 2 and 3? Well, you might say that we can study the logics induced by taking these different satisfaction clauses and then argue about the plausibility of the induced logics. However, 1 and 3, if you take 1 and if you take 3, you get out the same logic. And this has a pretty simple axiomatization. All so just substitution instances of theorems of intuitionistic propositional logic, and then the single modal axiom this implies put the box on the side. And then so axioms, rules. So modus ponens and necessitation, which is just that if you can deduce A, then you can deduce box A. Oh, I should say 5. It's just a time. So yeah, like I said, taking 1 and 3 together with the usual clauses for the non-modal connectives, we get the same logic.
I have a question.
Yep.
Is it 1 with 2 equals 3?
Yeah, good question. My notes does not tell me.
We could even put it in this nice way. 1 plus 2 equals 3.
That would be nice. So in my notes, I've just put the 1 and 3 together. 1 and 3 give the same logic. So I'm gonna hazard that it's no 2 here.
But as you mentioned, if you don't have 2, then
then we don't have. Yeah, so actually it must be 2.
it must be with 2. Yeah.
Yeah.
Just to fix.
Yeah.
So assuming 2, probably 1 and 3 are also equivalent, right?
Yeah.
Yeah.
Oh yeah. So that kind of makes sense.
Right. Yeah. So up until now, we've just been considering the diamond-free fragment. These, so 1 plus 2 and 3 come apart if we add in the diamond modal. Oh.
Oh. They'll get wet.
Okay, so just as with box, we could build in a condition so that monotonicity still holds with diamond in the language. So then we get I'm finally satisfied for all. Is this a such that unfortunately we don't have the nice analogy between there's no analogy between this and existential quantifier as there was here with universal, but that's just kind of an aesthetic feature more than anything. Let's do this form. So then I'll note that 3 and 4, taking 3 and 4 together, induces quite a strange logic, or at least one that doesn't meet all the requirements that we set out here.
Could we go with the definition of 4 again?
Yes.
Where's the W on the right?
W prime is greater than W. Yeah, the first V should be a W.
Oh yeah, sorry. Is that better?
And do you mean V forces 5?
Yeah, so just no V prime.
That's no V prime.
Well,
I think it's right.
It's a bound variable, and they're all D prime,
yeah,
so it's okay.
Okay.
But you could remove all the primes as well.
Yeah.
Yes.
Okay. That I didn't see the prime in the first.
Yeah, sorry.
Okay.
Okay. So in particular, requirement 3 fails if we take 3 and 4 together. That is adding the law of the excluded middle does not give rise to a classical modal logic. So how about another, then we have V. But for monotonicity to hold, we need to add a further condition. This is that if W prime is greater than or equal to W, which is related to V, then there exists V such that V wait, no, okay. W on V, V prime, V prime, V. So I guess we've got multiple different combinations to try, but I'll just note a few. If we take 1, 2, 5, and 6, which might seem fairly natural, we build in these frame requirements as opposed to in both cases. Then we actually fail requirements 4 and 5. For example, you can derive.
So can you explain 6?
So let me just check I wrote it down right first. What was that?
So this is the condition that's in rod W diamond 5.
It's the condition that if we have this, then there's always a V prime.
It's again a condition similar to 2.
Yeah, right. Yeah.
It's a frame.
Frame
It's something on the
condition,
frame. It's a frame condition.
Yeah.
So for a square,
Like 2.
like think of the worlds as being two-dimensional, so you can go
Yeah.
ordering in the world reachability direction, and then somehow these squares can be completed.
Cubicle.
Yeah.
Yeah, actually.
Yeah, no, okay.
I could. I'll draw these squares later. Actually. Well, very soon.
Up on the left. If you go up on the left side of the W, then
And you can also reach something.
yeah.
If you can go up and you can reach something, then
Yeah.
there's a common thing.
Exactly.
Yeah.
Yeah.
I guess I'll just draw these now. No, I'll get ahead of myself. Yeah, so you can derive this. The usual kind of duality between box and diamond. That's taking 1, 2, 5, and 6 together. So the 2 satisfaction clauses, 1 and 5, and the frame conditions 2 and 6. Okay. One more approach before we get on to the main approach. We take 3 as a satisfaction clause for box formula, and 5 for diamond. And then we impose the following 2 conditions, which I think are just the ones I've got down, but now I'll draw the boxes. So
6 is also very close to bi-simulation. It is
Yeah.
maybe that R is a kind of bi-simulation relation with respect to the ordering. Since,
Okay.
We can come back to this.
I don't want to disturb, sorry.
Okay, yeah.
It's an interruption.
But so, yeah. Okay, so we don't need force. We'll draw them up here. Wash. Dry. Yeah, so here's the boxes that I probably should have drawn already. So if we have this, this is, yeah, I think this is 2. Then we get, there's a v prime here that's greater than or equal to v, and
I think this is 6.
Yeah, this
oh, is it?
Yeah.
Okay.
R.
And that's an R. So this is 6.
Yeah. And 2 is yeah, you can draw 2 now.
Yeah, sure, John. So, yeah, it's just W.
I think the way you had it is you have the W, you have the W prime and the W, but you don't have the V yet. So it's the lower, the upper left, the top and the left, they're solid. You have those to begin with. And then it's the bottom and the right part that's dashed.
Bottom and right.
Yeah. Yep. Okay, there you go.
Yeah. Okay. Yeah. Yeah. I think what I did was I'd written these like, and then I just got confused about the
transpose the diagram.
Right. Yeah. Okay. So monotonicity holds, and there's also kind of a nice. So this is 2 then. Also kind of a nice justification for this informal. That is in cryptology and semantics for intuitionistic propositional logic, principal logic. Atomic facts accumulate of this partial order. So you might think it's reasonable to have the fact that some world W sees another world V as one of these facts that could persist. In which case we'd have, W prime sees V. But at the same time, we might have collected more facts about V. So V might have evolved to some V prime. And then, this turns into the condition that W prime can see V prime. So I guess that's a nice justification if you're happy with the fact that some world sees another world could be something that persists at the partial order. Okay, so then the induced logic here, I will write down an axiomatization of because it's actually the one that no, that's the blackboard. I'll write it here so we have it. It's relevant in the future. So the following system, A is before, B is before, C, which is going to say that not possibly false. Okay, and then rules as before, so just pronouns and necessitation. I'm going to call this IK. So you can show soundness and completeness with respect to what did I say? The semantics here. Just the fairly standard, I guess, canonical model method. Yeah, so I've got this here because it will turn out to be the logic that's induced by the natural deduction system of Simpson. Right, yeah, so that's a survey of some earlier approaches. How am I doing for time? I had no idea when I started, so how am I doing for time?
Let's give you till you started 1:40, so let's give it to 2:40, so 22 minutes.
Okay, maybe I should go faster through that. All right. Okay. So this is Simpson's approach, and it's quite nice. So the first sub approach that I mentioned takes seriously the Kripkean interpretation of modal logic, but it notices that there's nothing about the interpretations of formula per se that induces a classical modal logic. This just results from taking a classical meta theory. So I'm going to define a
It's this one.
Okay, so define a translation between modal formulas and first order formulas in a language LM, which contains one binary relation symbol R and then a predicate alpha for each proposition in the set class of primitive modal propositions. So then the translation goes, it's known as the standard translation. So, and this world here, think of it as the world from which we're evaluating the modal formula. So translation of a primitive atomic modal formula just goes to okay, maybe to save time. True goes to true, same for false. With the Boolean connectives, so it kind of does what you'd expect. you kind of see where it's going with the connectors, right? You just kind of divide over. So I'll skip to the modal formula. So the translation of diamond is that exists an x prime such that x related to x prime and x prime holds. Box. You might be able to guess if you spotted this. X implies so we introduce a new fresh variable when there's modalities involved. And as you can see here, the translation codes up the Kripke satisfaction clauses for box phi, diamond phi and box phi being satisfied. With classical modal logic, we have that a modal formula is a theorem if and only if the translation into first order logic is a theorem. Classically a theorem. So you might think the same relationship should hold of intuitionistic modal logic and intuitionistic first order logic. So the statement is by the statement of that analogous thing would be and then if you can prove intuitionistically that sorry, yeah, no. So what I said before wasn't quite right. Let me just write it down and explain. Okay, so classically we have that phi is a theorem of classical modal logic if and only if classically instead of intuitionistically you can prove this. So this is just the intuitionistic analog.
IK? Because now you have a
no. So this is a
specific case where there's no condition on the frame.
So this is just provability in intuitionistic first order logic.
Yes.
But the IML.
The IML. I mean, now it's kind of like a K modal logic where the.
Oh, okay. I see. Yeah, you're quite right.
Yeah. Okay, good.
Yeah.
And you just define precisely a system IK, whereas the IML is kind of like a whole.
Yeah. It's a whole class of
things. Yeah. Okay.
Yeah, so I guess this is anticipating that. So we want to prove this for the system that we're going to look at. It's anticipating that IK is the logic induced by that system. But yeah, this is what we're. So I should note that we can also.
Is this true?
This is. We'll get to this. Essentially, yes. Yeah. But I'll be more precise. And yeah, this equivalence is given the name meta-theoretical soundness and completeness. The idea is that we've kind of formalized the satisfaction clauses for modal logic, Kripke style, and then done this translation, and then we want to prove this formula intuitionistically. So in that sense, it's kind of a formalization of the formalization of the meta theory. Yeah. So we can also handle logics determined by a class of frames. So we take a sublanguage of this that just contains the binary relation, and then we determine the modal logic of T frames as that whose set of theorems is of the form where T is just a set of conditions given in the language R, the sublanguage of Rm. This just has this binary relation symbol. So a few things to note, drawbacks, or really just things to note. Some conditions that you might be interested in are not first order definable in this sublanguage that I mentioned. An example is Solovey's logic of provability. Another thing to watch out for is that some classically equivalent conditions will come apart intuitionistically. So you might have to make a choice of which is the right condition in some sense. But and then another drawback, which really is more of a motivation for giving a natural deduction system, is that here we're kind of just understanding the relevant intuitionistic modal logic in terms of first order logic. We'd like some way to understand it just in and of itself. So that motivates giving a system of natural deduction. So let's look at that. So the basic judgments in our system are going to be of the form x, phi. We call these prefix formulas, and you should be thinking, you should be reading this as phi holds at world x, intuitively. So the rules for standard non-modal connectors are going to be just the same as the ones that we're used to, aside from the fact that we're going to prefix formula. So just to give an example, so and introduction just becomes yeah, so how about modal formulas? We want the introduction rule for box to express that if phi holds at every world y, say, visible from x, then box phi holds at x. So you might write this down as under the assumption that y's are related to x. If you can derive that phi holds at the world y, then we can derive that box phi holds at the world x. So this is, and then we can discharge these assumptions. A condition on this is that y is distinct from x and does not appear in any open assumptions that the conclusion depends on, except this one here. So then the eliminate. So this is box introduction. Then the elimination rule will be constructive. I'll write down. I'll just write down the rules for diamond. Should be able to pass them, given that we've gone through the case for box, and then the elimination rule. Both of these you can just use. Yeah, so it's kind of like what you might expect. Okay, let me try and speed through some stuff. Talked about the other connectives. Yeah, so just as before over here, we can handle logics that have specific frame conditions. So, for example, we might require that the relation on the worlds be transitive. In which case, you'd add a rule if you have that x are y and y are z, then under the assumption that x are z, if you can derive something well, w, then you really have that conclusion. Yeah. So then there's an example derivation that I'll just skip. Okay, is this? I'm sorry to be rushing through this. Is it kind of clear? You know?
No question.
Yeah.
So there's two kinds of judgments you're using in this vector?
Yeah, so I should have said, yeah, two judgments, prefix, these prefix formulas, and yeah, judgments of the form x, r, y. Two types of judgments. Derivations, we impose the condition that they end in a prefix formula. So we only want to deduce things of the form phi holds at x. But we're allowed to use these judgments in our own conclusions. Yeah, sorry, I should have said that.
Thanks.
Is that right?
Yeah.
Okay.
That's why that explains why this transitivity rule is kind of implicit. I mean, if you could have conclusions of the form x r z, then you could just have the two premises on the left and the conclusion be x r z. But since you can't have that kind of thing in the conclusion, you have to parameterize over.
Mm-hmm. Yeah, sorry.
Thing, yeah.
I should have said, yeah, derivations and the prefix formulas. Yeah. So this natural deduction system we'll call n box diamond, and then we may or may not have conditions in T. And we say that this generates a consequence relation of the form of this form, where, so I'm seeing which definitions I can reasonably skip. So we know what T is. Gamma is going to be a set of prefix formula. G is a graph, so a structure of this form. Sorry, I'm trying to. Yeah. So so the graph G, you can just think of It contains it's kind of a classical model of T containing variables that occur in gamma and in this formula here. I'll define a couple of other things quickly. A graph morphism f from G to G prime is a function f from x to x prime such that x r y implies f x r x and y are in x. What else should I?
Well, you should try to wrap up to a conclusion because you're almost running.
Okay, all right. Let me see if I can do this in the best way possible. So, yeah, so I was giving you a consequence relation that's induced by this natural deduction system. Okay, how quickly should I wrap up to a conclusion?
Let's see, in about 3 minutes.
Okay. Okay, so let me just say then that there's a notion of a T model, which is just a Kripke model of the form WRV that makes use of graphs and graph morphisms as interpretations. You can prove soundness between this consequence relation and that notion of satisfaction. And then I guess I should probably say something about the equivalence of these two sub-approaches just to finish, because Patrick did ask this. So we prove the equivalence is a proof of the equivalence of these two statements. Phi is a theorem of n T and so this is the equivalence of 1 and 2 is if you accept that this the logic induced by this is IK. I mean, what we had originally written down was metalogical soundness and completeness with respect to IK. So if you trust me that this IK axiomatizes this, then this is our statement of metalogical soundness and completeness, and thereby the equivalence of these two sub-approaches to intuitionistic modal logic. Yeah, I guess that's nice.
All right, well, thank you here. And we'll have some questions for you.
Yeah.
Okay. Anyone wants to? Mark?
Maybe I would like to add something to that list
Mhm.
and then ask you whether that holds or not. Is there a double negation translation from IML to CML?
From IML to CML. So
I think that is something, a reasonable thing to on the wish list, to have on the wish list.
yeah, that seems reasonable. Certainly not. It's certainly less vague than some of the, or at least one of the conditions. I didn't come across this in reading, but
Yeah, so it's a kind of
it'd be
this question.
yeah.
I think the answer is Yes, so you know what it is? It's one of the possibilities is
Yeah.
prefixing every disjunction by double negation and every existential quantification, but we are propositional, and so that we don't have to do that here. And then here I would say prefix every diamond. That plausible guess, isn't it? Prefix every diamond by double negation. And then one would hope for, if the formula is provable in IML, then this double negation translation is provable in, no, the other way around. If a formula phi is provable in CML, then its double negation translation is provable in IML. The hope that it's true stems from the fact that we have the standard translation, which is kind of soundness and completeness but then we have to see how this double negation is, how it ripples through the standard translation.
Yeah. I think it's certainly a reasonable.
For example, if the standard translation of the double negation translation of phi is the double negation translation in intuitionistic predicate logic of the standard translation of phi. Just, in other words, that double negation translation and standard translation commute.
Yeah, but that was okay, at least for the propositional fragment. So there's a hope that that could work.
Yeah, so it might be fun to sort that out.
Yeah.
I don't know. But.
Yeah.
Any other questions?
Slightly off topic, but is this Alex Simpson the Alex Simpson that's currently at Edinburgh?
Yeah, although I think he moved very recently.
He moved to Ljubljana.
Yeah.
Yeah, I mean, there are many different approaches to intuitionistic modal logic, and this is one of them, where you try to stay very close to the frame interpretation of what the meaning should be. But there are, of course, many others. For instance, I don't know, did you look into the properties of this natural deduction system? Do you have a nice normalization result or normal forms? Or?
There's a normalization result, which I think is used to. So this, what I didn't get around to saying was that there's a semantic proof of this equivalence, but that's classical, requires a classical method theory. But there, I think there's also a intuitionistically acceptable proof that goes via this normalization result.
And of course, a completely different approach is to forget about these graphs or these relations and just try to say try to have some other meaning in mind and then give a proof theory. And that's sort of a whole other development. Sort of Frank Frenning here in the department did some, computer science did some very good work on that. So it's worth looking into. Okay, let's take a break, 5 minutes, and then we'll do mine.
Yeah. Good timing. Maybe join you?
Yep, we're just taking a break.
Okay, great. We're just sitting there, I don't know. Break, I think so. Yeah. Is anyone here? No. Sorry to miss your talk. Let it go.
Yeah, I forgot I was a little bit rushed again, but
That's all it is. It's hard to get the entire logic of whatever.
yeah.
Let's see if I can see. Is that your outline right there, 1 through 6?
These are conditions that you might want of an intuitionistic modal logic.
Yeah. What were you using as your main reference for intuitionistic modal logic?
So the main reference was PhD thesis of Alex Simpson.
Oh, great. Okay. Good resource, I guess.
Yeah, we were just talking about that in the question period. It's very different from the other things we've been looking at. But I mean, this, if you want to stay close to the frame semantics, then that's kind of what you want to do, right?
That's kind of what Alex was doing.
Yeah.
But it's a very proof theoretical study, isn't it?
Yeah.
Maybe I'll speak with you.
Yeah.
Does he give semantics
Yes, he does.
for first order or for propositional?
Proposition. I didn't get right down to this, but as far as I got,
Right, that's okay. We did some work around here on first order intuitionistic modal
I
logic.
guess the ledge doesn't get cleaned very often either.
Oh, now it's
Been cleaned to state for some time.
Yeah.
Koei Kashida, he wrote actually a whole dissertation on it. We did there's a topological approach. It's, of course, the underlying treatment is category theory, but then in the end we disguised it as topology.
I was gonna say, so I have to go
So
to
we
the
extended
Okay, yeah.
Tarski, McKinsey,
we
Tarski,
should touch base like next week about done stuff.
Yeah.
propositional as well.
yeah.
To first order,
Um,
using spaces and sheaves and.
yours went to next.
And then
Let's see, my
we did a kind
presentation
of
is
cryptized
26th, I want to say.
version using
Yeah.
appreciation.
So sometime.
Got two
Is
students who
that,
worked on that, and there's a master's
yeah.
thesis in our department, and
So,
then another master's thesis from
yeah, maybe
Germany.
Wednesday.
Came out of that.
Send me an email.
If you're interested, I
And may I have
have some pointers
wide
to
open
where
space time for that will be available.
Okay.
I haven't done any more lately, but
Thank you.
it's something that was in the works 5 years ago.
Yeah.
Before the hot.
Yeah.
I'm going to use that one.
And you have,
Have some scratch.
I have some longer colors for you.
Yes, but I had some. Green and red I had.
That's it.
That's enough. Oh, great. Yeah, good one.
Sure, there's something like to talk about. Yes, yeah, but it's very interesting stuff.
I'll try to remember to send you some pointers, remind me of that.
Yep, thanks, yeah.
Oh, you have a whole one. That's
All the
nice.
colors you want.
Yeah, right.
Actually, we've been doing a modal hot related to this.
Yeah.
Well, I don't know what I'm pointing to now, but related to intuitionistic modal logic. There are kind of two sides. You can do a monad, which is a box, and a comonad, which is like a diamond. A card and
You get spill water here, which is soaking the erasers and.
Yeah, so this time I took them
I
out.
think if we, yes,
the
it's-
monadic side.
this is
the
still,
second,
if we make one
the-
sweep there, it will, or you have some.
There are some interesting combinations of those things. You add the modal operator to the type theory rather than as just a propositional operator.
Right.
You have the modal operator in the whole type theory, and then it acts like a functor on the category types. It's not just an endofunctor, but a monad or a comonad. You can do something like that algebraic structure as a type constructor. Introduction and elimination of all that machinery.
We're missing them.
Every time I come here, it's a different size group.
Okay.
Yes, I will carry out a tiny part of Brouwer's program. Which is one of those grand endeavors. Well, at least it started as one of those grand endeavors in which one redoes all mathematics, but then based on intuitionistic logic, which is basically, for most people, constructive logic, so ordinary logic without the excluded middle. And for some, including Brouwer, this involved also extra axioms like the continuity axiom or bar induction, which for Brouwer was an extra axiom, but it is classically true, which the axiom of continuity is not. So, and we will carry this program out in combinatorics, and I hope to come to a result in infinite combinatorics called the infinite Ramsey theorem. Yeah. Right. So there are basically 2 questions before you start on something like that. So why do you do that? If you are not like me, you're not a believer that this is the only way to truth, which of course for Brouwer was the main motivation. And so so why do it? Well, there are more models actually. That is my main motivation. So there are models in which all function. So your results get, if you do not postulate extra axioms, your results get a larger, greater generality. So you can interpret them in domains where all functions are continuous, all functions are recursive, and so on. That gives, and I value the fact that the constructive proof has a computational content, so that you can. So you have, we must acknowledge that very often you have to work harder, but there is also a payoff of that hard work. And that is in the form, for example, of greater generality, or including a computational interpretation of your proof. So, but there is a more skeptical question. Why not? Why not? Since there are actually very few people doing this who are completely convinced that this is the only way to do it. And maybe it's best to postpone this question. I think that after my talk, actually, so you will you will have an idea of why not as well. So, but it's not that I so intendedly it was kind of anti, but it is it's really hard, and it becomes so fiddly that it is difficult. There are many more choices, and to make the right choices is hard, and it comes with considerable technical difficulties here. So what I shall do is first the finiteness of subsets of the natural numbers. That is the first topic. And so then they're basically, so by taking the natural numbers as the base set, so to say, we made already a choice, which is relevant. It's not, you're not only interested in such finite sets, of course, but so we have a decidable equality in M. This is, but we will consider both decidable P and non-decidable P, and I will. So there is no assumption, a priori assumption that all those P's should be decidable. In the paper that I gave you, in the oldest one, this assumption has been made. There, all the subsets are decidable. In the second paper, which is still a draft, this assumption has not been made. And here it should always be clear, and otherwise ask. Yeah. But I have some few notational issues. I will also use Pn for n in P if that's convenient. And I will use decidable P for all n. In n, I don't write that always. Pn or not Pn. And I will introduce concepts of finiteness and relations between them. And then this is stands for the fact that for every P, the ith notion of finiteness for P implies the jth notion of finiteness for P. So that can be probably best seen as a schema. So over all P, since we are interested in the relative strength of the various notions of finiteness. So, yeah. And then that there is some difficulty here constructively. It's not only constructively that finiteness is difficult, since I think everybody knows that finiteness is not first order definable. So that there is also in set theory there's some there's some variance, and there has been a history of proposing notions of finiteness, and they are not all of them equivalent, but if you have enough choice, then they become, and in classical logic, then they become all equivalent, I think. That is, but here, certainly not. And the first one is the one which you could say, which you could call it listability of the elements of P. So that is the strongest one that I know of. That means that P is finite if there is a list which enumerates all its elements. So so this is number one. So this is the strongest that I know, since you get all the information. You get all the elements enumerated in L, and so you also can count them, since they are natural numbers. You can count them, so you could make this L free of duplicates, and then you have. So that is at the same time. An observation is then that we immediately get. So this is a weak point of this otherwise nice and strong definition, is that every P which is finite in this sense becomes decidable. So it only works for decidable P's then, or it makes the P decidable. That is the. The second one does not have this property. So here comes the second one.
And that's because the list over n are decidable?
Yeah.
And we already know that.
Yeah, we can just do. Yeah, well, this is the inductive definition of lists, and you can just use the member function, or which is well defined. Yeah. So here the second one, that is now you get less information, you get an n such that beyond n, there are no elements in P. So now you know only an upper bound to elements of P. You only know an upper bound. So this is, one could also argue that this as a notion of finiteness is too strong, since it gives you much more information. And here, you know only, and it's, unless P is decidable, it is on the basis of this information not possible to find out what the elements of P are. So this is a weaker definition, and so we get yes.
If P is decidable, then they're equivalent.
Yes,
Then
that's true.
Yeah.
Yeah, but we can do even a little more. So so we have maybe I use this for my notions of finiteness and this for remarks on them. So we have, of course, this. And we have also that what Ulrich says, that if P is decidable, and then we can reverse. But now we can also ask the question, how much stronger is this notion of finiteness as compared to, so question, how strong is this one? So this one actually it would be more conveniently to use my, actively use my notations I abbreviate. So how strong is the converse of that? And the answer is that the converse gives you already the law of the excluded middle. Yeah. So that it means that it's really a whole lot weaker. And so how do we do that? We can define for a given proposition Q, we can define a very simple proposition P depending on Q by n equals 0 and Q. Now, we obviously have fin2 of PQ. We can just, so there are never elements larger than 0. So we have, so then, with n equals 1. And now, if we would have this converse, we would also have fin1 of PQ. But what does that actually tell us? That means that we have a list enumerating all elements of PQ. And then we can just test whether 0 is in this list or this list is empty. And so there, this L, I think I don't have to write that up. to save a little time. See, everybody sees this. Yeah. So we have that this converse is actually equivalent to the law of excluding. Now, of course, a question arises. What do we actually want? Now, there's a new question. And then you have the obvious, so to say, non-informative answer that depends on the application. Yeah, so what do we want? But there is, it's possible to give more informative answer. That is, the answer is basically closure properties, natural closure properties that we would like to have it to have. And so what closure properties would we like to have? Union, for example, we want to have that union of two finite sets is finite, and that's okay for both. Yes. Then
The empty set should be fine.
yeah, the empty set should be finite. That's a good one. Yes.
Singletons.
You're adding singletons, and adding singletons,
Oh, yeah.
but that's included in this one.
That kind of seems like enough already.
Subset.
Well, do you want it or do you not want it?
No, that depends on the application, but it's worth mentioning.
Yeah.
I would say subset closure on your, and it is also worth mentioning since it is distinguishing the two.
Yeah.
Now, since that is the difficulty with this one, which by the way is the equivalent as in the hot library. It's in the hot library they choose the type is finite if it's equivalent to the finite initial segment of the natural numbers, and then it's equivalent to this one. Also makes the type decidable, and it comes with a couple properties, and but also doesn't have this closure property. Since if you take for example, if you intersect P with an arbitrary predicate Q, then it's not longer possible to enumerate the intersection, since you wouldn't know what to do if Q is not decidable, which elements of L to throw in the list for P intersection Q. So that is one that is, and then what is intersection is also okay. Yeah. So this is but this is the one which is actually a little inconvenient that we don't have it for this otherwise nice property. Yeah. So then, well, what would be nice if I could systematically develop this and could present to you a whole lattice of finiteness concepts, and with all their interrelations and possible interrelations, and if an arrow like this doesn't hold, maybe I can give an axiom which is sufficient to prove it, like LEM was in this case, or even equivalent to such. It would be nice, but that is not the case. That is, I can't do that. We are not in a position. So, but I could. The idea is to explore this a little bit until you get bored. Probably beyond that point already, but but you're so polite that but not to not to so to stretch it too too far, so there will be some in the middle. 4, 5. Yeah, well, no, don't worry. I will kick out some. Yeah. So, but this is at least the weakest. The weakest that I know is the negation of the strongest way to say that P is infinite. And the strongest way to say that P is infinite is that I know is that there is an injection from N to P. So this is F injective. You could, but that is replace injective by increasing, strictly increasing, strictly.
They're saying that if you replace that, that's equivalent? Or?
Yes. Yeah. Since every strictly increasing is injective, and if you're injective, an injective function has an injective sequence, let's call it. It has a strictly increasing subsequence, also constructively. Okay. And the reason is the first element is the same, and then let's say that's 13. Then you know because of injectivity that you have to go not more than 13 steps ahead in your injection to find a new element, and so on, and you can define that by induction in a decent way, and that is and then it is equivalent. So that is these two are equivalent. Yeah. So and then there is, but here we are, so to say, this is after some suitable encoding still arithmetical, and here I'm quantifying over function. So I'm working in an extension of, for example, Heiting arithmetic, which is called the elementary analysis. Yeah, so where you can express this. So of course, there is this one has a smaller brother, so to say, or larger since it's slightly stronger, which in an arithmetical way expresses that P is constructively infinite, and that is this way. Yeah. So this is in words. This is called P is constructively infinite. But this is arithmetically expressed.
Maybe you could say unbounded.
Yeah, that's also a good. Yeah. Constructively unbounded. Yeah. Since this is a negation, so you have to, so to say, it's not that it's not bounded. It's, yeah, constructively unbounded. It's perfectly fine. And so also here we can, of course, we get that this is easy. Of course, since if we have an injection, then we can get this. So if this is not true, then such an injection cannot exist. And in this direction, we have to. So we have to. Let's say we have to refute. If we were to prove fin 8 of P, we have to refute this, and then we can refute it if we have such an injection, and we can make that, but we need a little bit of choice. That is AC 00 is sufficient to, and maybe, but I didn't check that, but it could be equivalent, but at least it is sufficient. So here we, on this end of the spectrum, we have this, but here we are in the realm of the negative formulation. So they give hardly any information. And the point is, well, are there still interesting formulations in here? And so in the first place, we should connect the negatives with the positives. And the easiest way to do that is to observe that fin 8 is actually not fin 2. Since the manipulation, the Morgan-like manipulations you need for the quantifiers are exactly those that are allowed in intuitionistic predicate logic. Is everybody need? And so then, of course, you also get that. So then you get that this one implies that one. Fin 2 implies fin 8 for all p, and you also get, not immediately, that the converse does not hold, since a formula like fin 2 is obviously not stable. It is not equivalent to its own, to the prefix with double negation. Probably the simplest way to see that is that you can craft a p, even a decidable one, such that this here, so that's it, you get instances of Markov's principle. So yeah, so we could say not fin 2p implies fin 2p. Yields Markov's principle, and Markov's principle is known not to be constructively valid. And here, to do this, you have to craft a suitable P.
On the other hand, if you have Markov's principle, you get
Not for decidable.
Yeah, for decidable.
Yeah, for decidable you get it then. Yeah, for decidable you. Well, no, since this is still not decidable even for decidable P. Yeah, no, still it's still stronger than yeah. Since this is by this quantor it is not. This is not a decidable predicate of n.
Yeah.
So then here is a digression which I will not do. So there is an interesting in between, which is fin 3. As here you know an upper bound to p, but it is possible to express that you only know an upper bound to the size of p, cardinality of p, and that is for example this one. So for any list of elements in P, there is some size such that if the list is longer than this size, then the list must contain a duplicate. This is now again, if you you go from 2 to 3, it is it's obvious that that is an implication. and one can ask, but maybe I would rather do this Ramsey thing than using a lot of time on this. But so we have that the converse in the converse F3 implies F2 implies LPO, the limited principle of omniscience, and it is since we allow. If we only allow decidable predicate, it's equivalent to LPO, and if we also include undecidable peaks, it's stronger than LPO. So I skip that. I skip also fin4, but I come back to fin4 if we have enough time after the infinite combinatorics. Since this one is suggests actually a more positive variant than this one, namely for all f from n to p, there exists a pair ij, I smaller than j, and that I denote in this way. So I have another notational device here, which is so this qualification is well, makes it possible that I get everything within some reasonable. Well, that is what here. What is to stand there? Yes.
But it should be
And. Oh yeah. Sorry. Yeah. Sorry. Yeah. And here it is this duplicate. This idea of duplicates. Which is a positive variant. So this is Dedekind finite, negatively formulated, and this is Dedekind finite, positively formulated. And it is it has reasonable closure properties, but not everything you would like to have. And the closure properties are harder to prove. It is implied by those, it implies those, so it is the ordering is but I would like to talk now about this interesting generalization which yields the infinite Ramsey theorem. So maybe I by now do away. That one was wet. This one is good. Do away with this stuff here, and so I'm going to state and prove the infinite Ramsey theorem, since I do not expect that everyone knows that by heart, but it's quite possible that you have seen it already. And if you have a good memory, then then you will immediately recognize it.
Can I ask about one other one before you go on?
Yeah, sure.
What about the analog of 9 that uses surjectivity rather than injectivity, where you say that you cannot have a surjection from P onto N?
So you could say that positively. So for every F, that's a good suggestion. This is not exhaustive at all. You see, this is maybe so for every F from P to N, there exists an N
Yeah.
such that for all k and p,
Yeah.
fk and fk is not p, is not n, sorry. So this is, yeah, good, thanks. Yeah, we can, yes, I don't, this is certainly,
That's F sub n. Fin sub n.
is it maybe, wait a moment, if
Is it one of
it's,
those?
is it one of, is this one? But there is of course also this one, not exists, an f from p to n, such that for all
Okay.
n in n, there exists a k in p, such that fk equals n.
Yeah, there's that too.
So we have to work on that. Yeah, thanks. Yeah, I'm not, this is, is good, thanks. Yeah. And I'm going to also to prove it, and this is, for the non-believer, you see this proof offers a diabolic pleasure of, so to say, it's provocative in, it will, but this is, I hope there are no true believers that get offended by this first proof, but then so stay on, so to say, hang on, and since I have, for this one, I have an intuitionistically acceptable alternative. Yeah. So every k coloring of the set of m element subsets of n, which is in that world they have they sometimes use this notation for that. So this is the m element subsets. There is an infinite A and now monochromatic. An infinite monochromatic A. So what is an infinite monochromatic A? That means that all the m element subsets with the elements taken from A, they have the same color in the coloring. So okay, so now I'm going to prove this informally and classically. So then I do it in this way. I start by enumerating n, and I start by 0. I'm going to construct this A. It is an obscene construction, but it is, you see the, so at 0. So now I look at what color, so wait a moment. We do it for k and m both equal to 2. So we have 2 colors, red and green, and we consider pairs of different distinct natural numbers. this is now 2-element sets. So this is, and so we can, for every 0, form such a 2-element set with all the positive numbers, and they all have a color. So I can, so to say, this is now the color that they have with 0. So I can have a red, and then I have again the green, and the red, and 2 reds, and then green, and so on. This is now comes the classical logic is for at least one of those colors occurs infinitely often. That is the pigeonhole principle for. So let's say that red. So infinitely often red. Let's make it's classically we know that it could be both, and then I have to choose. But I can say always choose the first color if both occur infinitely often. So if then I eliminate, I will not look at the numbers that are green with 0. So I kick them out, and I only keep the infinitely many. So in any step of the algorithm, I keep an infinite subset of the natural numbers. Mm-hmm. And now, because this we have red here, I color 0 red, since it is red with all the elements of the reduced set. So it is red with this one, this one, this one, and with all the infinitely many that follows, and the greens one are eliminated. So now I go to the next one. This is this one, and I analyze what color it has with the greater elements that are still in this infinite set. So maybe you see it coming already. Let's see that for some weird reason. So it is infinitely often green now. Then well, that does not make. Let's say that we have here another red one with 0 now on this level, yeah, and that it's infinitely often green. Then I kick out. I keep the ones that are green with 1 among those that were red with 0. And I kick out all the others one. So this one will now be kicked out, and so on. But I keep an infinite subset of the natural number all the time. And after this step,
you throw out 0 now.
No, I only look to the right. Oh, yeah, I only look to the right. Okay. Yeah. So no, it's only looking to the right. That is. So here I don't have something. I start, and now I continue with this one, and only to the right. So I have, so that is the diabolic aspect in the informal proof. I continue. I do this omega many times. So you see, if I'm applying omega many times the infinite pigeonhole principle, yes. But then, so to say, to make clear that you see, I don't care about it, I do it once more. I do it once more, and then you see, since now of the elements that are left, they have one of 2 colors. So one color occurs infinitely often among them. And so at least one, and the others. I pick just one that occurs infinitely often. And that is the monochromatic, infinite monochromatic set. Yeah. So that is, so this it looks as non-constructive as possible. You see, of course, the formal proof is not omega plus 1 times Pigeonhole principle. You do a decent induction and so on. You do it probably twice or 3 times in the base case, the induction step, and at the end. So that's it. But now try to make constructive sense of this. And the idea is to generalize this. So now I define, I have no good name for this. So now constructively. I have no good name for the predicate, and it is, I call it therefore co question mark. It is co something. So this is, and you will, it will become clear. It is that for every f from n to n, there exists a pair I smaller than j, such that R of fi and fj. So fi and fj are in the R relation. So this is the property, and it generalizes this one. You see, you could have here n and move the p here and then generalize to an arbitrary relation. And so now for the moment we are reasoning classically. So so classically, so explaining the name of this predicate. So what is co something R saying? It is, so in the first place, by taking for this f a constant function, we get that R is reflexive. So that is, but what we also get is that the complement of R does not admit, the complement of R does not admit a such an A, which has the same color. So let me make that precise. So R bar admits no R homogeneous or R chromatic and R colored infinite set. Do we is it clear what I mean here? So an R-colored infinite set would be a subset of the natural numbers, such that for any two elements that you pick from that set, then we would have that R bar holds. And this is the complement of R.
I don't quite get it. What is for a relation S, say, what is an S-colored?
Yeah.
Which all elements are estrogen. All pairs. Every pair of that set.
Yeah.
That's helpful.
Yeah.
So the right-hand side says there's no R-colored infinite, R-complement colored infinite set. That's what you mean by admits no.
So let me define this precisely. Let's call this one A. That means for all AB in A, A and B are different. Then we have that this holds. This is you cannot have such a set, since if you had it, you could classically enumerate. You would classically get it as the image of a function f, and then it would violate this. And so that is the. So, but you see that we're getting close to the infinite Ramsey theorem. Now, how do we connect this to the infinite Ramsey theorem? We do that given a two-coloring of N2, then we can define an R and an S that both include the diagonal so and both are symmetric. And with intersection, exactly the diagonal. So how do we do that? That's not at all difficult. So the coloring of N2 is basically ordered pairs here in the lower triangle. That's N2. So we have colors here. Those are red and those are green and so on. And then of course we take R and S accordingly. But since it must be symmetric, we add also those points and also those. And we give the diagonal both colors. So they are both in R and S. And then you have exactly this, that the diagonal is in both. They are by construction symmetric. And since coloring is a partition, their intersection is empty, but for the diagonal, of course, where they are, so to say, that is per construction, included in both.
And the union should be n squared.
Yeah, the union should be n squared. Very good. Yeah. Ah, I forgot this one. Good. Yeah. And now, we do not have, obviously, we do not have that the intersection is co-something. So not so if we could now prove in this situation that either R is co-something, is not co-something, or S is not co-something, then we get exactly the, so this is the infinite Ramsey theorem, since this premise is fulfilled. And this means, classically, this means that R bar, R complement, admits an infinite R colored ZA, or S complement admits such an S colored set. So that is the monochromatic set in the infinite Ramsey theorem. So so this one as a whole is an equivalent to the infinite Ramsey theorem, classically. And but now what we what we can do is to show that co-something is closed under intersection. If we show that co-something is closed under intersection, then we have something which is equivalent to this one. Classically, yeah, right. And so and this is provable in constructively. So this is so this is provable constructively. In elementary analysis plus bar induction. You essentially need bar induction for this. So and that is, so to say, coming back to the that is, so to say, closing the circle. So this is an example of Brouwer's program. So if you have here you have a theorem which is classically true, then find a statement which is classically equivalent to this one and which is constructively provable. Now, I think it was Flores who once had a very clever remark. He said a few weeks ago, he said, okay, well, if this is a theorem, it's a tautology. So, wasn't it?
Well, I had the same thought like half a minute ago. So
yeah, okay, yeah, it was probably, yeah, so it was. So, and the tautology is constructively provable, you see? This is, so what is the point of Brouwer program is, of course, that it's not only the denotation. So in the Phrygian, it's not only the denotation of this, but it's also the meaning. So if the if the classical tautology is for all x, px implies qx, then you want to have an equivalent to px and an equivalent, let's say p prime x, and a q prime x, such that constructively you can prove for all x, p prime x implies q prime x. And that is more or less, well, it's a little more difficult than that, but that is so that the denotation is still all the time this truth value true, but the meaning is, well, if not preserved, it is okay, more or less, at least classically the same. The meaning of this one is not true value 1. See, it's the, okay. Yeah, this week is now I should finish.
Yeah,
Wrap up. Yes, okay,
yeah.
it is fine. Yeah, I'm done. This was the main. We could. This is. Yeah. So it was. Since this is well, just in favor of Brouwer's program, I think that this is in elegance. This property is an important structural property of, and this in elegance, it can match this theorem. It doesn't have this compelling intuition in terms of colorings and monochromatic sets in the first instance, and that is so. But this diabolic, this proof, so to say, which is nice. You see, this is hard work, several pages hard work.
Oh.
Yeah, this is Thierry. This Thierry did it with in the early 90s. With this, I did this for decidable R's. I did it in my thesis in '86, and later with Veltman generalizing. And Thierry came in the early 90s up with an inductive version of this. You can formulate this inductively. That is related to fin 4 that I did not do. And then the proof becomes also elegant, both the statement and the proof. But the meaning changes. It's not the same. And he doesn't use bar induction, since the induction is not necessary, since it's built in the inductive definition that he uses here. So that is, but it's very elegant proof also. Yeah.
Yeah. Thank you.
Why is it called co-something?
Since it's about the complement has some. So if you do it for increasing functions, and you do it one-dimensional, it's co-finite. Yeah. Then it's R is co-finite if every increasing function there is an iso such that RFI holds. Yeah. And that is, yeah. So I have no better name for it than for the moment. Yeah.
I mean, this issue about being equivalent to a tautology, if it's classically true, one way to go around it is to find a very weak meta theory over which that doesn't prove the theorem, but still proves the equivalence.
I'm not sure I understand you.
So the issue with trying to come up in Brouwer's program with a classically equivalent but constructively provable version of something. You say there's this problem that, okay, you could just take the tautology, it's classically equivalent.
Yeah.
Right?
Yeah.
But if you have something that requires some logical strength, then perhaps you could find something that is equivalent over a very weak base theory that doesn't prove any of the two versions, but still proves that they're equivalent, and then prove constructively that one of them is provable.
Yeah, yes, that's
So no classical
possibly,
equivalent, but
yeah.
some theoretic equivalence?
Yeah, no, even stronger than equivalent because it's equivalent over using very little machinery. Right? So instead of just being, say, you have something that you can prove in CFC or something like that, and then suppose you could just prove it in pure logic or prove it in primitive recursive arithmetic or something like that. Prove the equivalence there. That doesn't prove any of the two versions, but it proves that they're equivalent using very little machinery, and that way that gives a very strong notion of being equivalent, right?
So, but then you would like to have not this one, since this one is classically equivalent to this one, and not by no means constructively.
Oh yeah, but classically maybe, but not using any arithmetic or any comprehension principles. But maybe,
you may use classical logic in this.
You may use classical, but maybe you don't use any strength, logical strength.
But maybe this example qualifies for since you don't need so much.
You just
otherwise than
pure logic.
So it's not so much more than So this may satisfy that, and that is probably could be a good methodology or guideline to But this also gives the difficulty of Brouwer's program and why it. So the question, why not? Recall my question, why not?
Yeah. Why not?
Well,
That's why not.
pick your favorite one, and if you for every application have to pick another one, this is not that is not nice. That is not. It's so fiddly. It's so sensitive to the particular choice there that it's.
The quote by Van der Waals, it says, "Intuitionist mathematics takes unhealthy concentration."
Unhealthy concentration. And who said that?
Van der Waals.
Van der Waarden. Ah, yes. Okay, good.
He said,
Yeah.
Brouwer's mathematics takes unhealthy concentration.
Yeah, this is. Van der Waarden was also Dutch, yes, but he went to the US, I think. I think he went to the US.
So in constructive set theory, one doesn't restrict attention to subsets of natural numbers.
One does not.
One does not restrict attention often. One is more interested in sets in general.
So you do not directly have access. Which one would be your favorite?
And there the two notions are the thin one and a notion of finitely enumerable, which are both equivalent to subsets.
Yeah.
So finitely enumerable when you're not insisting that you have a discrete set.
And you accept that this makes then the set decidable.
Yeah.
Membership becomes decidable of the set.
Yes.
Yeah. Equality does not. There's a difference between a decidable membership and decidable equality, of course, which you do not get. So such a list could have duplicates. Or without knowing it.
Yeah, so there are two notions. One is the having finite cardinality, the usual notion of it's equivalent to.
There's a bijection with. There's a bijection from.
And the other is you can enumerate the elements.
You can give a finite list, but you may not be able to remove the duplicates. Yeah.
And often in doing constructive set theory, it's the finitely enumerable one that plays a more is often used as the key one.
Yeah, but I think this one finitely enumerable makes membership decidable, but equality becomes not decidable. With the other, I think it's the other way around. If you have a bijection from the first n natural numbers to your set, then you can you can decide both.
Yeah.
You can decide both membership and equality. So and you never use one of the weaker ones, since this is also
Oh, in the literature of intuitionism, Veldman has
Yeah, sure.
all sorts of theory of, as you probably know,
Yeah, sure.
all sorts of theories of different notions of finiteness. In general, not just for subsets of natural numbers.
Yeah. So this is this is joint work with Veldman. I only had it for decidable relations, and so.
Okay, thank you very much.
Yeah.
Van der Waerden did his dissertation in